Okay, so I think we can start. So tell me also if you hear from home. And so welcome to everybody. And it's so good to see so many people here and also from home. And so I'm really proud to welcome you to this event. And I'm Leonardo, and here with me there is Mark. And we are QubiTO, the quantum computing team of Politecnico. And 100 years ago, there was a lot of new papers and discoveries concerning quantum mechanics. Maybe some of you know of the story of Helgoland and Werner Heisenberg. And 100 years ago later, we are here to celebrate these really important discoveries for humanity.
Okay, so we, as QubiTO, we are a very small quantum computing team, but we ask ourselves, how could we celebrate such an important feat for humanity as a whole? And we, among all the challenges that we do, we indulge in many hackathons, which are competitions around the world, and we do also some quantum computing projects. We came up with the idea of this little event, these 3 days, where we could celebrate and embrace research, discoveries, and engineering in just a span of 72 hours, basically. So I welcome you all to the first edition of the QubiTO Quantum Days. Applause. Okay, so without further ado, I would start this evening, this first evening of the QubiTO Quantum Days. I would like for you to help me in welcoming two key figures and characters for the QubiTO Quantum team. From one side, we have our advisor of the Master in Quantum Engineering, which was won 2 years ago here at Politecnico di Torino. And we have Professor Matteo Cocuzza. And the other one is the advisor of the QubiTO student team as a whole. So, which is Professor Bartolomeo Montrucchio. So please help me welcome them right on the stage. Hello, boys.
Okay. Okay. Okay, good evening. Nice to see you all, both in the room and through the remote connection. This is Matteo Cocuzza. I'm the academic advisor for the master degree in quantum engineering of Politecnico of Turin. The title of this presentation is, let me say, a little bit bombastic, but the aim is quite simple. I mean, is to provide you with an overview about this master degree, how it was conceived, and what is the present state of health of this master degree. Well, the Politecnico of Turin is investing a quite relevant amount of resources in not only in terms of money, but mostly in terms of human resources for research and training in the quantum field. Okay, even if not exactly in chronological order, we have in the academic year 2022-2023 the first Italian second-level master in quantum communication and computing that lasts a couple of seasons, that was addressed mostly to professionals from companies to improve their knowledge and their training in the quantum field. Then we set up a totally new and totally state-of-the-art infrastructure, research, and also educational infrastructure dedicated to quantum, that is PIQE. The acronym stands for Piemonte Quantum Enabling Technology, that is a sort of partnership between Politecnico Turin, the National Institute for Research in Metrology, the INRIM, whose unique site is here in Turin, and that is, of course, an added value for what concerns our activities in the quantum field, and also the University of Turin. So the core of this infrastructure is a clean room that we exploit for research activities, but also, as I will show you, for educational purpose for our quantum students. But of course, what was missing was a basic training course in the field of quantum. And as a consequence, a couple of years ago, we decided to design a totally novel quantum master degree program, novel at least for Italy, because it was and still is the first and only master degree in quantum engineering in Italy. Okay, there are some similar master courses, but they do not release an engineering title in Italy. So there is just one, and it is the ours. So the ambition was to design a master degree training course in the quantum field for engineers. Okay, so with a strong application focus and with a strong multidisciplinary focus. And so to this aim, we had to put together and to merge different competences and different colleagues from physics, from mathematics, from electronics, and of course, from computer science. The access to this master degree quantum in terms of bachelor degree is open and in a certain sense free, so with no formative debt, from different engineering bachelors, mostly electronic, physics, computer engineering, mathematics, and the different declination of what is communication engineering, okay? But we also accept very easily students outside the engineering domain, for instance, from mathematics, computer science, and physics. Other students, for the curriculum of other students, we have to check student by student what is their exact background, and so if they are suitable to access this master degree without any educational debt. The aim of this program is to educate the future professional in the quantum field, so has to be able to be actor of the second quantum revolution. To this aim, we have, of course, to transfer a lot of information, tons, I should say, of information related to the basic knowledge, so the mathematics, the quantum theory, quantum mechanics, but all such transfer are always addressing the main target, the main objective, to transform all this knowledge into something that is practical. So into a real system that can be useful for the implementation of electronic, computer, and communication system in different, of course, application field and for different markets. To this aim, and through the courses and through the syllabus of the master degree, we aim to form and to educate for all the students 3 different training profiles. So they will become expert in quantum computing, in quantum communication, and quantum sensing. There are many other and different approaches all around the world. Several of them are very vertical, okay? So limited to a specific domain. We decided to follow this approach that 3 years ago was the most advanced and the most frequent model that we observe in the few European master degree that were available. Okay, so this is why we selected this transversal and multidisciplinary approach that, in my opinion, is a strong added value and a peculiar characteristic of this master degree. Which are the main characteristics? So how we teach this subject. Of course, the official language for the entire course is the English, okay? And the motivation is quite clear, to open to international admission that are strongly welcome. Of course, we have standard and classical lectures and classroom exercises, but we have also talk series that, as I will show you, are basically seminars that we use to invite professional or expert from different companies and academic centers all around the world. We have a quite wide portfolio of practical activities, both computational and experimental. To this aim, we exploit our standard computer science lab or electronic lab, but an important strategic added value for our students is the possibility to access very peculiar and quite unique facilities. Okay, I mean, it's not that easy, it's not that common to find in a university, for instance, a clean room dedicated to micro and nanofabrication where they can, in a limited manner, of course, but try to train and to improve their expertise in micro and nanofabrication. And above all, what is more important, we have on site a quantum computer, a very recent purchase of a 5-qubit quantum computer that our student can access directly and without any barrier typical of the remote connection to other type of worldwide available quantum computer. These are, for instance, this is, for instance, a collection of pictures showing some of our students having their practical lab activities. Okay, so you can clearly recognize in this picture the students working in the clean room, students in the computer science lab, students in performing some experiment in QKD and quantum communication. Okay. But as I told you before, the most recent and most important added value is the quantum computer. Okay, quantum computer that was acquired through a partnership between Politecnico of Turin, the Links Foundation, and again, the National Institute for Research in Metrology. This computer was installed this spring, okay, spring 2025. It's a 5-qubit from a European company, IQM. We are very proud, of course, for this strategic choice, and we strongly believe that it will be a very important added value for our students and also for our research activity. I invite my colleague Bartolomeo Montrucchio, that is much more qualified than me to spend a few words about this computer. So Bartolomeo, if you want to come. Before leaving the word to Bartolomeo, I would just to highlight the fact, an important fact about this master degree, more generally speaking. We are trying to set up a strong network in the northwestern area of Italy, okay? So whatever we do is conceived and performed in collaboration with the other academic center or with the other companies that are working on this field, because we believe that providing and merging an acceptable large mass around this subject will be important and strategic to produce advancement, not only research, but advancement, and provide always novelties and then solicitation to our students, okay? And this is another brick in the wall for our plan.
Okay, thank you for your invitation to QubiTO, which is a very important thing, I think, and really very important. And thank you to you all for being here. And yes, as Matteo just told, we are very proud of this new course, but mainly we are proud of our laboratories. So PK, because please note that having at disposal of the students a clean room is not common at all. And also it is not common at all having at our disposal a quantum computer, because up to now in Italy there are only 2 of them, and one of them is mostly experimental, while this is full industrial, and it is available to everybody, basically, okay? Of course, with some limitations, but... And you will see something about on this quantum computer tomorrow, right? On Friday. So you will see a demo, and hopefully, because just for your curiosity, 2 days ago there was a blackout here in Turin, and unfortunately the quantum computer has a problem. Normally, you have to heat things. In this case, you have to reduce the heat. And so the temperature will go up, and so the computer was not fully working, and now it's going down again. So I suppose that for Friday it will be okay again. And anyway, in my opinion, it is extremely useful. Maybe some words about it, because I don't know exactly. I suppose that you are also from other universities, probably. I don't know. Is there someone from University of Turin? No. Okay. So you are basic. One. Okay. And so this means that most of you are from Politecnico di Torino, right? Okay. And so the basic idea is that, of course, the quantum computer is very useful, not because it is a 5 qubit, because 5 qubit is a little one, so it's not so powerful after all, but it is very important because it is possible to test a lot of things directly. For example, we can do tests on the working principle, so we can test the decoherence time, just to do an example, because probably you know that quantum computers have a big problem. They can work only, in particular this technology that is a superconductive technology, can work only for a few microseconds. It seems very strange, but they can work only for maybe 100 microseconds, no more. Okay. After this time, they stop working, and so you have to wait again to use it again. It does not break, simply stops working. Okay. And so this means that you have to program it in a particular way and so on. But normally you cannot test these things directly, because if, for example, you use the IBM one, that is, please note, that is for free for 10 minutes for 1 month. So we have to thank a lot IBM for that. But of course, they cannot allow you to do some experiments that in this case we can do because the computer is ours. And so we can do other experiments, we can test a lot of other things. We can do some tests also on the electronics side, because in the master degree, we have the course on quantum computer, but we have also a similar, a twin course, let's say, on quantum hardware. And of course, it works on the hardware side of this path. Okay. This is the last one, no? No.
Okay, approaching the end of this presentation, as I told you before, we are convinced that providing a state-of-the-art, a continuous state-of-the-art, so an overview related to the quantum field and the quantum domain is a fundamental aspect of the education of our students. So we often organize different seminars with both Italian and foreign companies or academies to provide an updated overview in this field. One of the important aspects of this master degree consists in the fact that the students can select an internship, okay, that is actually a quite frequent choice for them, because they probably appreciate the fact that having a practical experience is a strategic asset for their formation. This is a collection of some logos of companies and universities where our students have currently or have had their internship in the last weeks, in the last month. And similarly is for the thesis. Okay, so there is a final thesis that typically hand the master program. We provide the students a network of companies, universities. They can get in touch to find the best subject they could select, but they are very active and they are significantly contributing in enlarging this network of contact. And this is very, very, very appreciated from your professor. Few numbers to get close to the end about the master degree quantum. In the first year, we enrolled 52 students. In the second academic year, it is to say last year, we enrolled 47 students. So the number is quite constant, homogeneous. 20 of them from Politecnico of Turin, 20 of them from other Italian universities, and 7 from abroad, with a quite balanced distribution between the physics and the computer science area, a relatively minority contribution from the electronic, and other 1 student, okay, 2%, but it was 1 student. A very brave students from another field, but just 1. This year, we have currently enrolled 52 students. So you see that number is quite constant, even if the enrollment is still in progress. So I suppose that we will reach 55 students. We got an improvement, an increase of the order of 60% of application from abroad and the order of 50% from Italian university. A very short comment, these numbers are, in my opinion, physiological and also in a certain sense sane, because as far as the number will be in a range between 40 and 60, we are able to follow exactly as we want our student. Okay, so like a student, like a person, not like a number in a sea of many hundreds of students were just numbers. Okay, so this is also for the organization of the practical activity. So this is a physiological number. I personally do not want to improve too much this number. I think that from 40 to 60 is good and is the same. The second aspect that I would like to highlight is that very often students don't know that this program exists. Okay, I mean, just because it is the only one in Italy, probably students from other regions give a look to the Politecnico Turing program because they know that there is avionics, electronics, mechanics. The quantum engineering is the very, very, very last row in the list. Okay, we should change the name in something like advanced quantum engineering, probably, because this way we will scale up the ranking. Okay. Few words also about the Erasmus twin track program and something more. Even if relatively young, we succeeded in fixing a couple of exchange agreements in the Erasmus framework. One is with an Hungary university, the Pázmány Péter Catholic University, and the second one is with the Technical University of Vienna. And if I'm not wrong, we had already 3 students that follow this Erasmus path. We are going to enlarge the portfolio agreement. Okay, is a long path, believe me. Okay, it's not like switching off, clicking on a new agreement. Okay, it needs a lot of weeks, a lot of months to arrange all the things in the proper manner. And in particular, we're going to negotiate new agreement with the KTH in Sweden and Universidad Carlos III de Madrid in Spain. Starting from next year, we will have a twin track major program between mathematics engineering and quantum engineering. It is a 2+1 to got 2 master degree titles. Okay, I think is a quite good variant. And we are working to strengthen the partnership with the IQM. IQM is the provider of our quantum computer, just to make something bigger than not only acquiring and purchasing quantum computer, even if I think that is quite bigger, 1 million of investment in a machine and 1 million of investment in infrastructure. Okay, so we are evaluating to join the National Quantum Science and Technology Infrastructure. Okay, that is a national consortium that involve all the most important actors in the quantum field. We are trying to extend the network of quantum companies. For instance, next week, I will be in Milan to speak with ST Microelectronics and QubiTO. This is, of course, not only for research, but also to provide new opportunities for our students for internship, for thesis, and also eventually for job opportunities in the future. If I can conclude by using this selection of the press review, this is a master degree program that is living a quite significant hype, but in the positive sense of this word. Okay, I mean, there is a lot of expectation, and this is good. From our point of view, we consider this master degree as a sort of an our creator. We are strongly involved, we are strongly committed. And what I can tell you is that we are working really every day to try to improve our product, to try to offer you a better product and a better service. Okay, so many other news will come the next month to increase and to enlarge the possibilities for our current students and of course for our future students that will be probably the one that will take advantage of all of our work. Okay, I think that this is more than sufficient. I used more than the time that was accorded to me. Okay, thank you a lot.
Okay, I never use lavalier. Very cool. Okay, thank you very much, Professors Cocuzza and Montrucchio, for your kind welcoming. And now I would start to talk about the main dish of tonight. The next guest is, again, not any guest to us. He's a professor of us. He's already told us the basics of linear algebra last year, so we could grasp the meaning behind quantum mechanics. And right now he's teaching us the most interesting facts about quantum cryptography, which is one of the main, more promising and more concrete applications of quantum engineering as a whole. So he's prepared a very nice lecture for all of us, which is going to touch the most unusual, quirky, funny points of quantum mechanics, of this very strange science. And so if you're ready to embark in this journey to the edges of quantum mechanics and hopefully back, I would ask you to welcome kindly Professor Riccardo Adami.
So thank you very much for the kind introduction. Now probably my talk will be very disappointing because already and will look quite flat. But so I was asked to give you an overview, sort of historical overview, but I'm not a historian, so I was asked to give you a more philosophical overview, but I'm not a philosopher. I'm a mathematician, so the most boring thing in the world. More precisely, I'm a mathematical physicist, so I will try to give you some hint in some directions. And so I thought a bit about the title. You know, in the scientific development, there is an oscillation between what is called the normal science and the revolution. So there is a paradigm which is well settled, and then there is a revolution. The revolution imposes a new paradigm and so on. But I think that in the history of quantum mechanics, and many times in the history of science, there is a sort of crisis between the paradigm and the dogma somewhere. So I will talk about what happens when there is a sort of para-dogma. It will be just a quick talk through the history of quantum mechanics. And I want to thank, of course, the organizers and this wonderful QubiTO. I hope the pronunciation is correct. And I found this symbol very well drawn and really wonderful. Block sphere, harmonic oscillator with the correct number of oscillation. And then there is also Torino. I really admire. Okay, so we are told that this is the first century of quantum mechanics. There is some arbitrariness in this decision. We will see. However, it's a good year. And in this century, quantum mechanics has revolutionized many, many branches of human knowledge. In general, I have to speak a bit in order to convince the audience that quantum mechanics really impacted very, very strong on our life, but they already told you and probably you already know, so I will be quite fast on this point. But of course, quantum mechanics is a physical theory, so it impacted on physics, but it created a lot of mathematics. I would say that most of the modern mathematics comes from quantum mechanics, from functional analysis to some algebraic geometry, differential geometry. There is a quantum logic. There is a quantum algebra, like quantum graph theory. There are quantum graphs and so on. So there is really a lot. Of course, chemistry, because Wolfgang Pauli, one of the most famous, most gifted and some says most arrogant pioneers in quantum mechanics, used to say that chemistry is a chapter of physics. Some say that he was claiming that because his wife left him for a chemist. But this is sort of a science gossip. And then also information science, as we saw before, of course, engineering, we are here, and also philosophy, okay, and much more. But in spite of being so widespread, in fact, of being so important, as a theory is very poorly understood. So probably you recognize these two pictures. Okay, these two pictures come from two movies of the same film director. Who is the film director? Christopher Nolan, okay? So the first one on the top comes from Interstellar. Interstellar is a science fiction movie. I loved it a lot. And it is based on the theory of general relativity. Moreover, most of the movie, most of the script was written by Kip Thorne. Kip Thorne is a Nobel Prize in Physics, if I remember well, 2018. He studied general relativity. So the movie is extremely rigorous. Whatever happens in this movie has a strong physical justification. Thorne wrote a book entitled The Physics of Interstellar, and he clarified that the only thing missing in the movie is the gravitational wave. And it was Nolan who refused to put the gravitational waves in the movie because he says that from the point of view of the film director, it was not so good. But then he regretted because in 2020, Nobel Prize together with Kip Thorne was won by people who work on the experiment LIGO, who first detected gravitational waves. So Nolan apologized with Kip Thorne. The second is a movie dedicated to Robert Julius Oppenheimer. And it is not science fiction, so the comparison is not correct, but in any case gives some idea. So it is a historical biographical movie, but of course there is a physical theory underlying, which is quantum mechanics. And the presentation in quantum mechanics, from my point of view, is really disappointing. It's really superficial. There is just a lecture, Oppenheimer and his students, and it is very short, and they say something very strange. It is a particle. No, it is a wave. Okay, what it is, I don't know. It's really, it conveys the idea that quantum mechanics is an absurd theory. It cannot be told. There is no storytelling with quantum mechanics, at least. This is the idea that conveyed to me. I'm convinced of the opposite. I'm convinced that it is possible, it is not easy, but it is possible to have an idea of quantum mechanics more than that. So as we saw before, we are on the verge of a revolution, if not a scientific revolution, for sure a technological revolution, which is called the second quantum technological revolution. You see almost in all languages there are very, very interesting publication in the last years with the title Second or New Quantum Revolution. But if we talk about a second quantum revolution, it is because there was a first quantum revolution. And the first quantum revolution can be told in many, many times. And I like to isolate three milestones. So first, the invention of the transistor. Second, the invention of the laser. Third, the invention of LED. And just for owing to these three inventions, we recognize that there is a lot of quantum mechanics here in this room, in every laptop, in every cell phone. There is no laser pointer, but no, there is a laser pointer also here. So there is a laser. Okay. And so there is a lot of quantum mechanics. So we can say that without quantum mechanics, everyday life would be extremely different, extremely poor. But this was the first revolution. Now we are about the second. So after this introduction, I will basically three points. I will very rapidly go through the history of quantum mechanics, showing that we can isolate two branches. One is related to the first quantum revolution and the other to the second. And then I will say something about foundation. Probably this is the most exciting part that was announced, but it will be very short. In particular, on the issue of locality. And here we will see a sort of interplay between heresy and Para-Dogma. And then the third part, since I'm a mathematician, the third part has some formula, some long formula. Okay? And then we go to dinner. So when we talk about history of quantum mechanics, the starting point, in my opinion, should be non-quantum, and it will be by William Thomson. Oh, sorry. Okay, it is the other way around. So William Thomson, probably you know William Thomson by his other name, Lord Kelvin. Lord Kelvin was a Greek physicist and also a great entrepreneur. And at some point, he gave a talk in 900, exactly in 900, on the state of the physics. At the time, people were very optimistic. The widespread feeling was that physics was closed, in some sense. We knew everything. So the scenario, the landscape was really sunny. There were just two clouds. This is my ability on drawing clouds, you see. These two clouds were the ether. So, you know, the ether was supposed to be the medium that conveyed the electromagnetic wave, so the ether here. And the other one, the black body radiation. So I really like this talk by Lord Kelvin because he was able to isolate the 2 points that would convey to big revolution. Because from the ether, first spatial and then general relativity was born, and from black body radiation started the story of quantum mechanics. And so at that time, the paradigm was the paradigm of continuity. So the radiation was continuous. So what Max Planck says in 900 is the first heresy. So the first point here at year 900, Planck. The first heresy by Max Planck is the following. If we consider a black body, if you imagine a black body like something black, you are wrong. It is not a black body. Typical black body is a star. Okay, something that it is in equilibrium. There is an equilibrium between matter and radiation. However, the black body was really discussed in the 19th century at a deep point. It was considered as a sort of universal system. It had a universal behavior, but it had a big problem. So if you want to compute the energy inside the black body, the energy was infinite. And this was a big problem for the theory. And Planck had an idea. Instead of considering the energy to be a continuum, continuously distributed in space, we treat the energy as made of small packets. This is the first time that the word quantum appears. This is here, Quantenstücken, chunks of quantum. This is sort of. And what Planck does is consider this structure, this discontinuous structure of the radiation, and then sum all the components of the radiation and find a finite result. This was really a very important result, but the point is that it was heretic because it wanted to recover the continuous paradigm. What he says here, so he says that he considered this continuous structure as a mathematical trick that he used because it was a desperate way out. Verzweifelten Ausweg. It was a desperate way out. So for him, it was just a trick. But there is another heretic at that time, a young guy whose name is Albert Einstein. 5 years later, he takes the same idea, treats the light as being made of quanta, not continuous, and explains, another very beautiful picture of mine, explains the photoelectric effect. The photoelectric effect, just you take a piece of matter and you send light against a piece of matter, and you are able to extract electrons from the matter. Okay, this is very easy, but naively, you can think that the most powerful is the radiation, the most powerful is light, the larger is the number of electrons that are extracted. And this is not true. This is not true. The threshold, the important parameter is not the power, but is the frequency, the color of the light. And this is really strange. What is the relationship between frequency and energy in order to extract electron? It was the relationship found by Planck. Every quantum had an energy that was proportional to the frequency. So Einstein was able to explain this effect that was not among the clouds of Lord Kelvin, but it was very important, and then he won the Nobel Prize for this in 1921. So here we are, Einstein, 1905. And then the third heresy is Bohr. It is important for many reasons, but also because we are passing from the radiation from light to the matter. Bohr says the atom, in order not to collapse in the nucleus very fast, must have only a discrete number of admitted orbits. And so he quantized the orbits in order to explain the spectra of the atoms, like hydrogen and so on. And so here we are in 1913 with Bohr. And then, you see, there is a big jump here. From 13 to 24, there is something which is called old quantum theory. In the old quantum theory, the methods are heuristic. People like those try to find a way to solve the problems and so on, but they don't get to any theory. Up to first in 24, we have to cite the contribution of de Broglie that says, where is wave, there is quantum, but also that where is matter, there is also waves. But then in 25, so 1 century ago, the famous Helgoland's paper, who was already cited, Werner Heisenberg performs one technical revolution. One technical revolution is that he's able to describe the mechanism of emission of radiation through atoms. And the technical revolution is through this, what is called matrix mechanics. Heisenberg used matrix, but he didn't know because he was young. He didn't know linear algebra. I was starting for being so obsessed by linear algebra. Heisenberg didn't know. And so he went to Helgoland and he came back with this really big computation and showed them to his advisor, Max Born. And Born says, oh, okay, but this is linear algebra. These are matrices. And Heisenberg said, what are matrices? Then he started studying matrices. He was clever. He learned. So this was the technical point, but there is also a conceptual philosophical point. Here Heisenberg states that the role of physics is to give quantitative relationship between results of experiment, between observable quantities. So he says physics is not a description of the truth, of what is behind. The very question, what is behind the observation, is without any sense. And in particular, it does not make sense to try to describe the possible orbits of the electrons. This is a big revolution. If we want to go to philosophy, so the key word is circle of Vienna. Okay? And there is a big influence. And then the colleagues of Heisenberg in Göttingen, Born and Jordan, developed a formalism, and the formalism is called matrix mechanics, but it is not very successful because it is very far from the mathematical sensitivity of the scientific community at that time. There is Pauli. Again, Pauli is able to reconstruct the spectrum of the hydrogen atom from this, but I invite you to read what Pauli wrote. It is incredible. Only Pauli could do that. The year later, so here in 25, we can say Heisenberg, Born, Jordan, and then 1 year later, a new guy appeared on the stage, and he's Erwin Schrödinger. Erwin Schrödinger says, okay, I can recover all the results by Heisenberg and more by writing this equation. So you see, this equation, okay, if you don't know this equation, it appears very complicated. But if you look at closer, it is easy, because here there is psi, the wave function, the unknown, what you have to find. Here there is 5, but there is no psi squared. There is no log psi. So this equation is linear. Linear, also in English, means easy. So in some sense, this equation is easy. But not only that, this equation has another important feature. It is a wave equation, and people were used to deal with wave. Water wave, electromagnetic wave. So mathematically, it was something close to the sensitivity of people, so it had a big success. And then the same Schrödinger proved the complete equivalence between Heisenberg quantum mechanics and his so-called wave mechanics, even though for the interpretation, Schrödinger was much more shy than Heisenberg. He was not satisfied. Schrödinger used to say, if this quantum jump really exists, I will really regret to devote my life to this theory. I really did not like the theory. And then the same 26, there is Max Born. Born solves the problem. So if a wave is the core of the theory, where is the particle? What is the relationship? Schrödinger believed that the wave meant that the particle was widespread. But then when you look at the particle is always at a given point. It's never widespread. It's a point particle. So what Born says, okay, it is not a matter wave. It is a probability wave. This is another revolution. Because in a fundamental theory, probability, randomness, appears. So even if we know perfectly the state of the system, we have to deal with some uncertainty. And this is really, really strange. And then, okay, there is a good formalism, and Born won Nobel Prize for this in '52. He was quite angry. He says, okay, but I did many things that are much more interesting than that. You cannot give me the Nobel Prize for that. But I think it was interesting too. He was a mathematical physicist. He wanted to win the Nobel Prize for something more mathematical. And then, so we are at 27. 27, there is the uncertainty principle. Again, Heisenberg uncertainty principle. We will talk about that. So I think you know, we are saying that the uncertainty of the position, the product between the uncertainty of the position and the uncertainty of the momentum cannot be made tiny as you want. So if you know very well the position, you know very badly the momentum and vice versa. And all this is systematized in the famous Chicago lectures in the 30, where starts the so-called Copenhagen interpretation of quantum mechanics. What we believe, what many people believe today in quantum mechanics, was born there. And in particular, there is one point. There are no physical properties. We are not allowed to talk about physical properties if we don't measure. They emerge in the measurement. And this is a main point. And then, okay, again, Dirac. And after Dirac, if I can go here, in 32, von Neumann writes down the rigorous mathematics. This is why, for a mathematician, von Neumann is an important milestone, but not only mathematics, because there is this word here in von Neumann, reduction. Reduction is what we call today the collapse, sometimes also reduction. So he says that there is something, there is a process when we measure that it is not possible to explain it through the Schrödinger equation. This is the meaning. Okay, I like to put the quotes in German for a historical fact, because at that time, physics, and not only physics, spoke German, but we are in 32. In 33, Hitler goes to power in Germany. And I was really always, and I'm still astonished by the fact that the country that was the most advanced, that was hegemonic scientifically and culturally, was able to do this jump. And then we will see that English will take the place. And then, okay, so we end here, and then there is nuclear physics, Fermi, Szilard, and all the other. I like to cite Lise Meitner. And here we have big science, Manhattan Project, and so on. Okay? But basically, the conceptual story of quantum mechanics ends here, and then here we have what we quoted before, LED, laser, transistor. So before transistor, then laser, then LED. So, and this is the first quantum revolution. This is more or less the story. But there is another story, a parallel story. The story starts in 1935. And so we are here, and the names are the names by Albert Einstein, Boris Podolsky, and Nathan Rosen. Okay, so probably you cannot, probably you can recognize Einstein, which is a pop hero, so everybody knows Einstein. So here there is a list of some months ago of the papers of Einstein with citations. The most cited paper by Einstein is not paper on special relativity, general relativity, not even the Nobel Prize paper about photoelectric effect, but it is another one whose title is Can Quantum Mechanical Description, blah, 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 considered complete? So is really questioning the nature of quantum mechanics. Is it a complete theory, like everybody thinks, or not? And notice that, this is not a scientific journal. It is the New York Times. When Einstein wrote an important paper, he immediately went to the New York Times. He was not happy at all, because this was not the correct way to talk about that. And it was Podolsky that sent a sort of letter to New York Times before the paper was accepted and published. So Einstein was a bit angry with Podolsky. But I'm quite surprised by the fact that what is written here, more or less it is correct, much more correct than what you read today about science in many newspapers. And so what is the content of EPR paper, okay? May I use, yeah. The content is the following. Suppose, okay, you don't know, you cannot know, like Heisenberg said, position and momentum of one particle. But if you consider two particles, and you say, I know the distance between the two. And I know, this was the situation, the total momentum of the two. These two quantities, distance and total momentum, can be known with arbitrary precision. Okay? Why? If you know a bit of quantum mechanics, you immediately say that these two observables commute. You can compute it, or you can reason in terms of relative and center of mass variables. They commute, so they can be known with arbitrary precision. Let me be more precise. It is possible to organize a state, a quantum state of the couple of particles, in such a way that these two quantities, distance and total momentum, are almost perfectly known. These are what we call today entangled states. Okay, entanglement is extremely important in the second quantum revolution. And now there is the reasoning of EPR, but we know that it was Einstein, the one who was really obsessed with that. Now, if you measure the position of the particle 1, and you know that the particle 1 is D, then you know the position of the particle 2, because you know the distance, it is D. On the other hand, if you choose to measure the momentum of the particle 1, then you know the momentum of particle 2. So, in principle, it is possible to say that particle 2 has a precise momentum and a precise position. Why? Because you measure particle 1, not particle 2. If you measure particle 1, nothing happens to particle 2. This is the key reasoning of Einstein. Is it clear? This is the only reasoning of the talk. But it is by Einstein, so it's not so elementary. It is extremely subtle. It is a 4-page paper, but I read it many, many times, and each time I discovered something I really did not catch. But now my interpretation is this, and more or less the symbols are the same. Okay? What is the principle which is underlying this reasoning of Einstein? And it is not hidden. Oops, sorry. It is not hidden at all. It is clarified. Their argument is based on the notion of locality, which is written in this way. Since at the time of measurement, the two particles are far away, they no longer interact, no real change can take place on the second particle in consequence of anything that may be done to the first. I touch the first, the second is very far away, the second cannot know. It's elementary. Everybody accepts it. Nobody questions the principle of locality at that time. But Einstein is the only one who say, okay, apply this to your quantum mechanics, and you see that there is a big problem, a problem of completeness. And so many years later, Abraham Pais, who was a physicist but also a biographer of Einstein, wrote, it is very beautiful. It is very beautiful, but on this point, Pais really didn't catch the point. But Pais says all the criticism of Einstein, you see this time it is in English, criticism of Einstein have never impeded, nor will they ever impede, the scientific development and success of the theory. Of course, never impeded, but what Pais didn't see, that instead of impeding, this paper gave rise to a big development, which is the second quantum revolution. Why? Notice that here we are in 36. Sorry, in 35, and we have to wait 51 to see a development by Bohm. Bohm is a very important, strange character. I would like to talk about Bohm. But Bohm says, okay, I take the argument of Einstein, I rephrase it in terms of spin. Probably most of you know this argument in terms of spin. It is not the original version, but it is nice in terms of spin because spin is a discrete variable. So it is easier mathematically to treat. And then there was Bell, who brought this qualitative reasoning of Einstein in terms of a quantitative inequality. We will see that. And then there were various elaborations of Bell inequality, but we are in 64, we are here. So, okay. Okay. I come here, so time is circular according to some philosophers. So 35 is also the year of Schrödinger's cat. Schrödinger talked a lot with Einstein and Szilard about foundation. And so Bohm is 52 and 64 Bell. And then there are many experiments, okay? And let me give a look to this experiment. So the core is to prove a formula which is called CHSH. Clauser, Holt, Shimoni, Hornberger, or Clauser, Hornberger, Shimoni, Holt, I don't remember. And the experimental setting is the following. There is a source of entangled photon, like the two particles of Einstein. One particle goes left towards Alice. Alice measures Alice, so this is a measure of Alice, of the polarization of the photon along a direction A. So Alice has a Polaroid, she takes the Polaroid in some direction and sees whether the photon passes or not. Then she writes 0 or 1. The right photons goes toward Alice's friend, Bob. Bob measures his photon along the direction B, the polarization along the direction B. But Alice and Bob can choose two directions, A and prime Alice, B and B prime Bob, arbitrarily and randomly, okay? And the idea is to measure the correlation between the two measurements. So what is the inequality? We have two binary observable, the polarization belongs to different directions of the polarization of the photon along two different directions. The two photons are spatially separated. And first of all, Bell defines what is basically a correlation. You see this function of two different directions, one direction for Alice, another direction for Bob. And it is the sum of coincidence, Alice measures 0, Bob measures 0, plus Alice measure 1, Bob measure 1, minus the discrepancies, 0, 1, 1, 0. It's a measure of the correlation. And then there is a strange combination. I never understood why Bell found this combination. And nobody explained me how Bell, probably just tried, asked ChatGPT. So this is this strange combination, and then the idea is extremely simple. It's astonishingly simple. If there is a locality hypothesis which says that the probability of having, for instance, the result 0 for Alice and the result 0 for Bob, or also 0, 1, 1, 1, whatever you want, but if the probability factorizes, so if the two measurements are independent, they must be, because the two directions are chosen independently, quite simultaneously, and they are distant, then this quantity B must be less than 2. This hypothesis is called Bell locality. Probably Einstein would have liked it. We don't know. Einstein died in 55. But this is a mathematical version of the hypothesis of locality, and then it comes out that this quantity cannot exceed 2. But if you go to quantum mechanics and you choose cleverly the state of the photon, maximum entanglement, and the direction A prime, B prime, you'll find that B can be much larger than 2 square root of 2. Bell, Bohm, everybody believed in locality. They wanted the experiment to give this result. But starting already from the early test by Clauser and collaborators, there is a violation of the Bell inequality. Sorry, I'm always confused by the arrows. Okay, violation of the Bell inequality, which means that this inequality breaks, which means that there is no locality. So there are many experienced, Clauser, Aspect, and Zeilinger won Nobel Prize in 2022 for this reason. There are very experimental details, and a nice chapter is how to choose independently the direction of the two polarizer. One idea is to take the fluctuation in the redshift for photons coming from a very far quasar. They are doing this in Canaria. And in Barcelona, they ask people which direction, independently, and they do like that. It is really, really incredible how to simulate a true randomness, but there is a philosophical question. Does randomness really exist? This is another chapter I don't want to touch. So, and now what you read in many books, Einstein was wrong. It is, I don't know, there are people who really enjoy to say Einstein was wrong. So, was Einstein really wrong? Of course he was wrong, because the principle of locality invoked by Einstein was disproved by the violation of Bell inequality. So locality is false. But all people at the time believed in locality. Nobody answered to Einstein, locality is wrong. Nobody was able to do that. Moreover, in being disproved, the contribution of 35 paper Pierre became even more important and led to discovery of this quantum correlation in the presence of the entanglement. Moreover, led also to hidden variable theories. I will not talk, I like very much this point. The variable theories, like the theory by Bohm. It's funny, if you go to the motivation on Nobel Prize in 2020, it is written that they won a Nobel Prize because they disproved hidden variable theories. But there is plenty of hidden variable theories, so probably they give them Nobel Prize without understanding why. And moreover, the seeds of the second quantum technological revolution are in EPR. So this is my opinion. The question whether Einstein was right or not, it's not so interesting. And then the second quantum revolution. There is an entangle-based technology that comes through the no-cloning theory. No-cloning theorem means that you cannot clone photon streams unless the photons are in either one or other direction that are both orthogonal. If you want to clone cats, you can clone an ensemble of dead and alive cats. But if there is one Schrödinger cat, you cannot clone. This is the idea. And this was proved in an incredible way by Giancarlo Girard, first in 81, and Eva Uter-Zurek, Dix, and so on. But the important fact is that through the non-cloning theorem, it is proved that you cannot use entanglement to convey information. And this is really strange. This was not clear to Einstein, was not clear to everybody until Girardi proved it. So we can forgive Einstein if it was not clear. However, you can teleport a state without copying it. You destroy the original and you teleport the copy. And you can use entanglement to make encryption. And then you can make quantum computer like the one that we have here. And so these are these two branches. This one, which is the paradigm. The other one, so this is second revolution. Second revolution that gives rise to what we study in our master, and that had to fight against some position like the position by Pies or Oppenheimer and so on. And it traveled underground from 35 up to us. And now, okay, would you like 10 minutes of mathematics or are you hungry? 10 minutes. 10 minutes, because I want to give you the flavor of something a bit different. There is another paradigm, which is linearity. Schrödinger equation is linear. Schrödinger cut works for cut, because the theory is linear. But there is also a sort of non-linear quantum mechanics. How is it possible? So first of all, you probably know, some of you probably know some non-linear regimes in quantum mechanics. The most famous probably is Hartree-Fock. There is also Hartree theory. And what I will talk about is the Bose-Einstein condensation, because it's something I worked on and I find it wonderful in physics. And Bose-Einstein condensates evolve with an equation, you see, which is very similar to Schrödinger. It is Schrödinger up to here. But then there is this other term. You remember what I told you when showing Schrödinger equation. There is psi, there is no psi square. Here there is phi square. This is a non-linear, and everything changes. And in particular, another interesting point, I will not go into deep, is that in quantum mechanics, it happens that a linear dynamics is approximated by a nonlinear one. If you know a bit of mathematics, this is completely crazy. In mathematics, in mathematical physics, you deal with nonlinear equations that are extremely difficult. And the first thing you do when studying it, you go and linearize them. You fix a point which is a nice point, nothing dangerous happens there, and you linearize. And then you work with linear. You are so happy. Quantum mechanics, it is the contrary that happens. A linear dynamics is approximated by a nonlinear one. But there's a big gain. The gain is in passing from many body linear to one body nonlinear. And then you can put this into a computer, for instance. Moreover, nonlinearity has a strange behavior. Remember what von Neumann said. He said that the collapse, reduction, cannot be described by Schrödinger equation. But by a nonlinear Schrödinger equation, it can, because nonlinear equation can provide a phenomenon called blow up, where all the information concentrates in one point. So, also from a foundational point of view, this is nice. And this is the Bose-Einstein condensation. I like this picture. This is a picture I have stolen from the homepage of Wolfgang Ketterle, Nobel Prize 2001. What is a Bose-Einstein condensation? This is a gas. The gas you learned at school, billiard balls, they hit together, and then you look at them far away, and this is a gas. Nice. But then you lower the temperature. Remember what Professor Montrucchio told us. If you lower the temperature, quantum regime goes better. If you lower the temperature, you see the famous de Broglie wavelength that I showed in slide number 7. And the de Broglie wavelength is proportional, is inversely proportional to the square root of temperature. So it becomes larger and larger. And here you see some quantum interference. Now you lower the temperature again, and a few Kelvin, there is a critical temperature that gives a transition. In this transition, you see there are particles which have just a larger de Broglie wavelength, but there is also a giant particle that suddenly forms and occupies all the space. And this is a phase transition. When ideally you go to the absolute zero, we are able to go very, very close to the absolute zero. Then you have this giant particle, and it is nice because it's like having a quantum particle with all the strange phenomena. It is macroscopic. You can use it. But it is nonlinear. There is this strange nonlinear term. And this is a condensation. You see, you start from the gas here, and then the gas condensates, and then you say, but why here condensation means occupy all the space, and why here condensation means to concentrate? Because here we are in the Fourier space. If you know mathematics, when you spread in position space, you concentrate in Fourier space, momentum space. It is the same. This is the worst. And I want just to tell you how mathematically looks the problem. You start from the linear n-body problem. You have a big wave function that depends on the coordinates of all. You write down a Schrödinger equation, which is very compact here, but it is enormous. It is enormous because these Hamiltonian operators are like an n square terms, and n is very, very, very big, like the Avogadro number. And then you consider a weak potential with a very strange shape. It is very strong, but very concentrated. Here, this potential is non-zero at a scale which is 1 over n. It is very strange. You imagine that the potential changes with n. This is a mathematical method. It is called scaling method. It means that you get the correct scaling of the potential, and then you go to the limit, and the limit captures the good behavior. And then there is a hypothesis which is called Stoßzahlen-Satz. Everybody understands. I don't know why it's called like that. It means a sort of chaos. Every particle is in the same state. It's a totally symmetric state. This is totally symmetric. Then at the beginning, then the system interacts. Everything mixed up. It is very messy. And then you take the limit for n goes to infinity. And here you have the so-called reduced density matrix of one particle, which is a wave function, and the wave function solves a nonlinear equation. So this is the idea. The idea, qualitatively, is that the nonlinear term is the potential of the other particles. Okay, so as a conclusion, historically, quantum mechanics, the result is not like, in Italy we say un uomo solo al comando. I don't know, relativity theory, it was Einstein was really leading. It was not really alone, but it was leading. Probably also classical mechanics with Newton. Okay, there was Hooke, there was a lot of people, but quantum mechanics is really collective. Many states, many people, many philosophies. And this is why it is so rich. And this is why I think history of quantum mechanics is really wonderful. And then there is several interpretations. So what is probably, if you're studying quantum mechanics, you get fascinated by, I don't know, Bohmian against Copenhagen, super determinist of many worlds, incredible things. In my opinion, for each interpretation you choose, there is something very counterintuitive to accept. There is not interpretation that says, oh, everything is clear. And this is the root of the fact that it is difficult to tell quantum mechanics. It can be non-locality, like in Bohm and ordinary quantum mechanics. It can be contextuality, which is an extremely subtle question. Superdeterminism, we are all slave of a machinery, and we believe that we are free, but we are not. Non-realism. In my opinion, the choice of an interpretation can be due to some philosophical attitudes. I'm super determinist. I don't want any responsibility. Everything is decided, so I like it. Or to convenience. What do I mean by convenience? I mean that when I started to learn Bohmian mechanics, I discovered that in Bohmian mechanics, some physical phenomena like decoherence, that we talked about, decoherence, are easy to see. And if you see better, you can prove more theorems. So it is convenient. But for other problems, it can be convenient to think in terms of many worlds. David Deutsch invented quantum computing because thinking in many worlds, he says. So. And then the strange fact about the last part, nonlinearity, I wanted to show you that some approximation can give up the constitutive feature of the theory, which is nonlinearity, but might help on treating fundamental questions. like going back from these effective models, which are not fundamental, but see that they provide blow-up, and probably they can help in understanding the measure. Okay, and this is all, and there is a last slide, and the last slide there are just 2 books. One of these 2 books is really beautiful, and it is this one by David Kaiser. I really like the way he reads the story. He doesn't write this, but it's really the line I like, the line that I follow. The other one, I don't know whether it's beautiful because nobody read it up to now. But thank you very much. Questo qua in genere si mette, se hanno domande li facciamo fare.
Sì, sì, infatti. Okay, I hope this...
But perhaps it's not.
Okay, so thank you again to Professor Adami for this very interesting lecture. And I wanted to say, if anyone has any question about the lecture, otherwise I have one. Okay, if I can, just one thing, I didn't understand really. The idea of nonlinear quantum mechanics comes from the observation that world is nonlinear, so we want nonlinear quantum mechanics, or to solve like the measurement postulate.
There are both lines, in fact. So what I know best is the line that says nonlinearity is a good approximation for linearity in spatial systems, in spatial regimes. So when you have this Stotz-Zahlen-Satz hypothesis, and then you can work it out. But on the other hand, there is the school by, also I cited Giancarlo Ghirardi. Giancarlo Ghirardi is best known not for the no-cloning theory, because very few know that Giancarlo Ghirardi was the first one. I learned it when I read this wonderful book. And the idea of Ghirardi and his group was to mimic the collapse by introducing some nonlinear term and a stochastic term, both stochastic, which means random, and nonlinear. So there are, if you want, both lines, a modellistic effective description line and a more fundamental line. Yes. I don't dare to say what came before because I don't know.
Thank you. So, if there are no other questions, I'd say that for the first day is on. So I hope to see you tomorrow, but thank you for coming today to the first day of the QubiTO Quantum Days. And so tomorrow there is Scott Aronson with his talk, and if you don't know him, he's really the truth about quantum computing, and it's pretty famous in the field. And so enjoy your evening, and bye. Thank you very much. Also bye to people at home. Huh? Facciamo una foto con tutti.